Hello, everyone. Welcome to QWorld Quantum Science Days. This is our second edition. Thank you very much for all of you for your interest. We have 3 days, 9 sessions. We have 33 contributed talks and 9 invited talks. If you join already Discord, all information you will need, it will be there. You will see the schedule there. Zoom links will be shared. All meetings will be on the Zoom, and you can ask your questions by commenting. There are also channels for talks in Discord. They are also ordered according to program. You can also write your questions there. The advantage of Discord is your question will stay there, and these speakers or authors can also answer them after some time. You can also communicate further with them. So if you didn't join Discord, still we sent some emails. Check also your spam folder. Probably sometimes it slipped to there. Also, all information is there. You can check the program on the web page. You can go to calendar, etc. Also, Zoom links shared with you. So I will try to keep this part short. We have more than 600, let's say, participants, registered people. Thank you very much. Half of them are already in Discord. This is very nice to see such appreciation and interest. Also, I would like to thank our organizers. Akash is here, Adam is here. Also, we have a PC of 11 people. I also would like to thank them. They really make the program very nice. If you notice, we have several different topics from different areas, and some sessions are even have its own thema, like this first session. And also, I would like to thank chairs. For the first talk, I will chair it. By the way, I forget my name. I guess I am Abu. I am one of the active member of the QWorld, also active organizers in this conference. Okay, as I told, the protocol for questions is you can write in chat here, or you can write in the Discord. We will collect them and ask the speakers. If there will be no time, we direct you to the Discord and you can continue your discussions there. So for the first session, we will start with Nathan from Unitary Fund. Unitary Fund is always special for us because they are supporting QWorld from very beginning. They are also supporting this event. And one nice thing in these sessions, you will listen some talks about quantum software, quantum error correction, error mitigation, and related topic. This is also exactly what Unitary Fund supporting with microgrants, or they have their own also research projects ongoing. Okay. So we will start with Nathan. Nathan, could you please share also your screen?
Yes, sure. And thanks, Abu, for the invitation and everyone for joining. So let me share my screen. Let me check. You have, you can see it full screen.
Yep, Nathan. So Nathan,
yeah, great.
Will be about quantum error mitigation on NISQ devices and simulators. There is already ongoing some software development about quantum error mitigation. I believe that he will also mention about this. Okay, Nathan, the stage is yours. Thank you.
Thank you, Abu. And again, thank you everyone for coming. Please give me a 5-minute alert when my time is about to be over. So I work at the Unitary Fund. I'm also visiting researcher at the University of Milan at RIKEN, which are Japan National Labs. And I'm really excited to be in this virtual conference. I think it's great what QWorld has achieved with these many events and activities. So the outline for this talk is the following. The main topic is quantum error mitigation on actual devices and hardware simulators. But I like also to give a kind of like brief overview of Unitary Fund activities, which I think could be very interesting for the participants of these Quantum Science Days. Then I will introduce quantum error mitigation with a focus on Mitig, which is a Python toolbox that we're developing at Unitary Fund with the whole community, providing an overview of error mitigation and Mitig, and then sort of like a deep dive into specific techniques. And finally, I would like to provide a summary of related research on quantum error mitigation that Unitary Fund is doing with partner organizations. So what is Unitary Fund? It's a non-profit whose mission is to create a quantum technology ecosystem that is as open as possible. So this is the reason why Unitary Fund has a focus on fostering and developing the quantum open source ecosystem, but it's not only limited to that. So as Abu was mentioning, we're really glad to be able to support QWorld, actually since even before 2020. So far, Unitary Fund has given over 50 microgrants, which are $4,000 grants, no strings attached, to explorers in the field of quantum technology. So it could be folks who want to build communities like QWorld or the Quantum Universal Education, or folks who are working on a specific open source tool like QLEAT, which is the topic of a talk in this session after my talk, or even more collaborative tools and projects also supporting education and research. So please have a look at unitary.fund if you wish to apply. Application is very simple. It takes 5 minutes, and there is an advisory board reviewing on a rolling basis the applications every month. And if the application is rejected, you can apply as many times as you want. So it's very simple, doesn't take too much time. So as you can see from these metrics here, pretty high focus is put on open source software, because that's a way we think that the projects can have the most impact, and on a so-called pre-competitive stage, so before startup creation. But even startups have been created out of Unitary Fund grants as a follow-up of this of the initiative, including like a no-profit like QWorld, which is now pretty big. So one of the core focus of Unitary Fund is to build what we see that no one else in the space is building. So it could be stuff that the academic side is not taking because it's focused on research papers, and that is not picked up by companies, startups, or corporates. And these are like long-term projects that Unitary Fund develops. And these are the two main projects that we are involved with. One is Mitiq, the Python toolkit for quantum error mitigation, which is the focus of this talk. The second project is Mitiq, and it's a community-driven quantum computing benchmark website, which you can check out at mitiq.info. So this is actually going to be the focus of Dan Stranol's talk in a couple, like at the end of the conference on June 3rd. And let me just paste here the link for the Mitiq website. But first, let me provide an overview of Mitiq. Oh, sorry for the hiccup here. There is something cut off. But basically, Mitiq is a platform to showcase metrics and add metrics and learn about the state of the art of quantum computing systems. So here you see a chart that is self-generated for quantum volume, just to know what is the state of the art in quantum volume, which is one of the metrics that helps benchmark the quality of hardware devices. There is a series of other metrics, not only on hardware, on application-oriented. For example, what is the best result against max cut by a quantum algorithm, or also like with specific simulation and compilation focus with classical devices, as well as error correction mitigation techniques. So on the left, you can see what the web page looks like. It's a scroll of submissions, but again, you can learn more about this project that we're really excited about at Unitary Fund in Dan Strano's talk on June 3rd. And let me emphasize that we think that it's important to be able to track the state of the art of quantum computing systems, to be able to assess how fast the development in the field is going, and also to understand where are the, like, open issues, challenges, or opportunities. So continuing on the overview of Unitary Fund activities before jumping into a deep dive on quantum error mitigation, Unitary Fund supports several established projects, as well as the nascent ones with the microgrants. The most famous of which is QTIP, the Quantum Toolbox in Python, which I will mention briefly with respect to qutip-qip at the end of the talk. I just wanted to show that QTIP is a tool to simulate quantum systems with over 700,000 downloads and a worldwide community of maintainers and users. So this community is meeting also on a platform provided by the Unitary Fund, which is our Discord server, which you can reach via the web at discord.unitary.fund or on your Discord app. And QTIP is not the only community open source project that is hosted at Unitary Fund. There's also others, including Mitiq, the Quantum Intermediate Representation Alliance, Penny Lane, and other projects, including Orchestra from Zapata. So yeah, have a look at the Discord. There is a bunch of channels also to get started in open source software development. But one special event that we designed to help onboard students, researchers into open source software development in quantum is starting actually at the end of the week on June 3rd, and it's called Unitary Hack. So Unitary Hack is a hackathon. It's fully online. Anyone can sign up, and it's a hackathon that is designed to support existing open source quantum projects from QTIP on. So have a look. I'm gonna paste here the website, which is called unitaryhack.dev. It's very easy to remember. And let me just give a brief slide showcasing a couple of the projects that are supported and showcased on Unitary Hack. And how does it work? You sign up on Unitary Hack and you have 2 weeks to browse these projects and find issues that are open on the projects that you would like to work on. And that is a way to get a reward in terms of like swag, any open issue on these repositories. But at the same time, we ask the maintainers, what are the issues that we would like to see solved by contributors at Unitary Hack? And so each project has roughly $300 that they split up in different bounties, so that if you solve this problem, which is connected to an issue on the open source project for this community, and the solution that you provided is accepted, you can claim the bounty in cash, and Unitary Fund will cover it. So my suggestion is to start browsing and looking at these projects, and if there is something that you can help with, Many of the bounties do not require quantum knowledge. So if you're a software developer or you know some Python or you know JavaScript, there's also like other languages such as C++, Julia in participating projects. Do not hesitate to have a look and sign up. So I have a last slide about supporters, and then I will start with a proper quantum error mitigation talk. And this is a list of a Unitary Fund corporate supporters. There's also like individual donors, but we have a set of supporters that help us with two like sort of like membership program tiers, core supporters and supporting members. And there's also other supporters that support our activities. And we also have several academic collaborators. This is a subset specifically with respect to Mitiq. In this case, also thanks to a Department of Energy grant through the ARQC program. So part of the research I will show, it's done by the Unitary Fund team together with these collaborators that you see on the right. So now let's do the deep dive into quantum error mitigation. I'm not even sure that everyone knows about this term, but I guess that most folks have heard at least about quantum error correction. So what is the difference between quantum error correction and quantum error mitigation? So let's say that quantum error mitigation is an approximate quantum error correction, or better, is a subset of techniques that are part of quantum error correction. But there are some differences if you look closer. So quantum error correction, of course, is something that many in the quantum computing community believe it's necessary to reach the level of scale that we need to be able to implement on quantum hardware algorithms that have an impactful effect on state-of-the-art problems. And this is also like, you know, connected to the Mitiq project I spoke about earlier. So the main steps in quantum error correction are that there are different logical qubits embedded into many more physical qubits. And there is a feedback loop based on intermediate measurements for so-called syndrome detection. And the correction operations are based on the measured syndrome. So there is a fast feedback loop that needs to be put into place together with these intermediate measurements. So once we will reach error thresholds on hardware low enough, this technique will be scalable. But right now, it's pretty much unfeasible with what you can do on near-term quantum computers, meaning the quantum computers that you can access on the cloud or in a research lab at this point. And together with the high level of noise threshold, beyond the threshold needed to implement, for example, a fault-tolerant quantum computing through quantum error correction. There is also this problem, technical problems, engineering problems, of course, of this fast feedback and engineering stack that has not been fully deployed, at least not for the devices that are reachable right now on the cloud. So what's error mitigation? Well, error mitigation is a set of techniques that is based on performing multiple and different quantum computations, knowing that they are noisy because they run on noisy computers or noisy simulators if you're interested in research. Collect the results once the quantum computer, the interaction with the quantum computer has finished, and then infer better expectation values close to the ideal values that should be the correct one of a quantum computation based on this collection of noisy data that is performed with a set of techniques that wants to be more clever than just running the quantum circuit, which embeds the quantum algorithm of choice. So asymptotically, this is unscalable. So for very long quantum circuits or very, let's say, deep quantum algorithms, this is not a very, it's not a feasible technique, generally speaking, because it has an overhead that you can see in the fact that these multiple and different noisy quantum computations have an overhead in the amount of jobs that you need to launch on quantum computers. But it is feasible on near-term quantum computers, and it's something that we can test right now to start to improve the quality of results on quantum computing measurements and jobs. Another important difference that one should point out, though, is that due to this process, which is sort of like a quantum sampling and classical inference step, it is possible to implement error mitigation, mostly, I would say, for all the techniques that I will discuss at least, only on quantum computations that require having an expected value of a quantum observable. So they're not applicable, most of these techniques, for in cases in which you need something beyond, like one-shot quantum computing applications, beyond expected values. This is not, there are some techniques such as dynamical decoupling that could also help in that regard, but generally speaking, that is the case. So I also want to flag this recent physical review letter paper by researchers at IBM, which is actually, I think, very interesting because it's basically trying to have the best of two worlds. And it's applying error mitigation to implement an approximate quantum error correction technique to lower the requirements and sort of like increase the thresholds that are quite limiting right now for quantum error correction. So hybridizing these two sort of like frameworks is also something very interesting from the point of view of research. So now let me get to the basics of running a quantum algorithm on a quantum computer. And we have a very simple way and general way of depicting what happens. There is a rho, which is a density matrix evolving in time according to, ideally, a noiseless time-dependent Hamiltonian that you see here, K of T. And this is basically a generalization of Schrödinger equation, and it's called von Neumann equation that works for density matrix formalism. So on the bottom, you see an example of this ideal quantum algorithm. You have two qubits on which one is applying a Hadamard gate and the C0 control not operation. So we know that if we make this quantum circuit, which is the simplest quantum algorithm that we can think of with some entanglement, with enough gates down the line, at some point, what we will see, it's what you see here, basically white noise. Everything that your measurement will give you in terms of bit strings, but even of measured observables, will be basically white noise. Ideally white noise, because if it's not white noise, there is also some correlated noise in your device. So let's take for a moment, again, stick to the theory and think of what is actually happening, the simplest way that we can think of what is actually happening. Because clearly, not only the noises Hamiltonian that we want to apply to the quantum circuit is happening, but there is also some noise that we can exemplify here with a noise operator or super operator acting on the density matrix, mathcal L, with a lambda noise scale factor that is a dimensional real number that signifies the intensity of the noise. So for noiseless evolution, the ideal one, lambda is equal to 0. Let's put lambda equal to 1 to the level of noise at which the quantum computer operates. So lambda equal to 1, it's the hardware level of noise. So what happens if we increase the noise? So that's quite counterintuitive, but that's the idea behind this paper, in which the idea of zero noise extrapolation was implemented. Well, if we increase the noise, the quantum computation, as I mentioned before, will decrease in quality. But what if we then increase the noise at different noise scale factors from 1 to 2 to 4 to 6 to 8, and then based on this sampling, we decide to extrapolate to a zero noise limit, which is unattainable from the hardware device, but to which we can extrapolate based on an inference technique. And in this case, we're just fitting these different data points that you see actually taken in an experiment that was done by the Unitary Fund team on an IBM Q Harmonic device. In this case, for a depth equal to 100 quantum circuit with randomized benchmarking task. So you see that we can extrapolate the zero noise limit. And in this case, based on the algorithm that we were running, this randomized benchmarking, of which the result we knew was an expectation value of 1, you see that the extrapolated zero noise limit based on this sampling is better than the single data point that we would have reached if we were only running the device at the level noise. So this is basically already encompassing an idea that is common to many quantum error mitigation techniques, which is sampling different quantum algorithms, generally increasing the noise or learning something about the device, and based on this information, sort of like extrapolate to the zero noise limit. So this was actually, so the experiment I showed is actually an experiment done with Mitiq, but let's say the first example that I know of zero noise extrapolation is this paper here that you see again from the IBM team, which is a Nature paper from 2019 by Kandala and co-authors, in which what they did experimentally is when they were applying these gates, of course, at the device level, you have continuous time pulses, or actually you have pulses, and they were stretching the pulses so that effectively they were increasing the noise level of a device because the pulses were slower and the device was undergoing, like the qubits were undergoing rotation on longer time scale, and quantum noise that was not controlled by these pulses was kicking in earlier on. But then when we were starting to develop Mitiq, which is a toolkit to implement zero noise extrapolation, which is this technique, which I just briefly summarized, and other techniques, we were wondering, well, pulse stretching that you see exemplified here in terms of these quantum circuit, ideal quantum circuit, and then the effective quantum circuit is something that is generally not available to the standard user who has access to cloud-based quantum computing devices, just because you're able to launch a job with a set of quantum gates in your quantum circuit, and you do not have control of the pulse level. There are also now devices that have control of the pulse level, but they also require an extra effort to be able to compile those pulses. So the challenge here was, are we able to develop techniques that can be applied at the gate level only? This is why we call these digital noise scaling methods, and in general, in specific digital zero noise extrapolation, but we'll also talk about other digital techniques. So you can see exemplified here 2 examples of what we call folding of a circuit, which is local folding, in which, as you can see, a single gate is repeated with the dagger and the gate itself. So you know that U dagger U is equal to identity. And all quantum operations in a quantum circuit, at least quantum gates, besides, let's say, reset or barriers, are unitary operations. So basically, when you are applying G dagger G, you're just applying the identity. But so from a logical point of view, this circuit is performing the same operations of this circuit, but it's much cheaper. So it's basically the contrary of optimization done by a quantum compiler, where actually the approach there is that you want to decrease the depth of a gate to be able to, make as many operations as possible before quantum noise kicks in and makes every quantum correlation work or be washed out. In this case, we actually want to decrease the performance of a device in order to be able to sample more data points and then extrapolate to the zero noise value. And here, in the case of global folding, you see actually the technique of folding, so of repeating the dagger and then the operation themselves applied to the full quantum circuit. So we developed several techniques into Mitik to actually allow users to implement these different folding techniques at the digital level, that is at the gate-based level. So now I can, now that I gave a brief introduction of zero noise error mitigation, zero noise extrapolation, and the digital zero noise extrapolation that was implemented in Mitik, I feel like I can give a brief overview of Mitik itself. So you can find more information about Mitik at mitik.readthedocs.io. There is a full documentation of more than 200 pages with a user guide and also API docs for each function. Mitik is distributed on PyPy, so the Python package index, so that on your machine you can just type pip install Mitik and you're ready to go, and you can start to play with examples of the documentation. So Mitik is a compiler, or let's say a toolkit, to allow to apply different error mitigation techniques. And I will provide some information about the design concepts behind Mitik. The main idea is that you should be able to use the framework of choice for the quantum algorithms that you want to write. So it is compatible, it's built on top of Circ, but it's compatible with Qiskit, PyQuil, Bracket, PennyLane, and also OpenCasm. I will talk, this is from the front end. So the language or framework that you decide to use to write the quantum circuit. With respect to the backend, Mitik is backend independent. I will provide a bit more details about this. And this is an overview of the techniques that we are implementing in Mitik. The first one is zero noise extrapolation. And there's also others that I will briefly review. Unfortunately, I think that time will be a bit, will be too little to really go into the details of them. But we have a thorough documentation on all of these techniques. Probabilistic error cancellation, Clifford data regression, and also most recently, something that actually we're writing the documentation about these weeks, digital dynamical decoupling. And here on the right, you can see a brief sketch of the Mitik code structure with all these different techniques, with the different sub-modules, and also these operational modules for benchmarking different circuits and for integrating with different interfaces, the ones I mentioned here in the front end. So how to use Mitik? What we thought is about the typical workflow in quantum software development and for users. So on the left, you have the different high-level quantum intermediate representation, or let's say quantum circuit representation framework that are available. There are many, and there is a lot of duplication. So there's we can feel the pain because we experience it ourselves, but rewriting an algorithm in different frameworks. So we want anyone who has their language or framework of choice be able to use Mitik and execute on a backend. And on the right, you see the hardware or simulator devices that are available to users. And then, as I mentioned before, you have generally an expectation value that you want to calculate with NISQ algorithms. So Mitik is applied in between. And here you see the name of the modules of the different techniques. And we want to show this symmetry between the different techniques in which you have many quantum circuits or noise-scaled quantum circuits. You execute on the backend, you collect the results, and then you perform some sort of inference. And in the case of DDD, which is digital dynamical decoupling, actually there is no inference because all you do is at the level of a different compilation. I will mention this technique at the end. So yes, I mentioned that with Mitik, you could apply folding in the slide before introducing Mitik. And here I just wanted to show real quick, what does it look like to perform this error mitigation technique in Mitik. It's very simple. So the top block here is just defining the quantum circuit that I showed in the first slide. And in the bottom here, we are importing from Mitik a scaling method, the one called for global folding, and we're applying global folding. And here you see the effect of global folding. So it's as simple as a single line. Well, this is a slide that is with respect to the inference techniques. So as I said, one set is the quantum sampling, or in this case, folding, and the other set is the inference techniques. So zero noise extrapolation was initially framed with the idea of applying Richardson extrapolation, which is an extrapolation technique. But there is also other ways of extrapolating data points. These are completely classical techniques, like from not even machine learning, statistics. And they're like linear fits, exponential fits, poly-exponential factories, or also like adaptive factories based on information on the results at different noise scaling levels. So again, taking as an example, 2-qubit randomized benchmarking quantum circuit. In the bottom, you can see results that were obtained and are reported actually in this paper on IBM Q London device and Rigetti Aspen 8 device. These are two superconducting circuit devices. And you can see that at one in blue, you see it's where we stop with at the level that actually this is like the ideal quantum circuit. This is the noise scaling. And then here there is the noise extrapolation. So actually one can, there's no shoe that fits all, no size that fits all. So in this case, we know that the correct result is one because we're applying a test circuit before applying the known circuit with a known result, like the circuit with a known result. And for example, in this case, for IBM Q, we see that exponential extrapolation is the one with the best fit, closer to one, which is the ideal result. In the case of Rigetti, we actually found that quadratic or Richardson extrapolation was performing better than the exponential fit. So over the past couple of months, there's been several tests of zero noise extrapolation on real hardware device, both from the Unitary Fund team, but also from users of Mitig. So that's also something great because through citations, we can check who is citing the Mitig white paper, which was shown on the previous slide. But it's also great to see folks really using Mitig. So here on the left, you see a blog post from the AWS blog by Ryan LaRose and collaborators. in which it was shown that in the case of mirror circuits, which are a specific set of circuits, using what is called in Rigetti verbatim compilation in bracket, which means that you make sure that the quantum circuit that you send to the machine is not further compiled. That's why it's from Latin verbatim, which is important to be able to know what is happening at this low level. Then we are showing here, well, on the top, the gain provided by error mitigation. And here you see without zero noise extrapolation, the bottom curve, and with zero noise extrapolation, the top curve. These are other results from the literature. Quantum devices are used for quantum simulation. For example, in this case, in the Center for Quantum Field Theory, to test, in this case, a plaquette model with frustration with respect to quantum field theories, but really compiling it to a very simple model with 3 spins interacting, actually 3 qubits interacting on a IBM Q hardware device. So this is a paper by Emily Huffman and collaborators that you can read. And most recently, collaborators of mine at Unitary Fund have shown how a metric inspired by quantum volume, which has been named effective quantum volume, based on the application of quantum error mitigation, can be implemented with Mitiq, increasing the effective quantum volume result obtained when running the quantum volume protocol on hardware devices. So you can read more in this paper here. And I'm also excited because just this week, I mentioned before that Mitiq is an open community with most of the development happening on Discord. So just this week, there is a student, Nick Gardner from Stanford, who's doing an internship on their project on Mitiq. He just implemented quantum volume test circuits, quantum circuits, based on some that are present also in CERC, that can be easily used in Mitiq for benchmarking. So actually right now there is like a function for a heavy bit string and also quantum volume circuits that can be generated in Mitiq very easily. So you can have a look in the API doc. So I guess that I have just a couple of minutes, and as always, I overshoot with the number of slides that I put in. So unfortunately, I will have to hurry up a bit and quickly go through some of these slides. I wanted just to give a glimpse of the different techniques that we have implemented in Mitiq. Another technique is probabilistic error cancellation. And again, this idea of sampling into a parameter space that is wider of that of just compiling the original quantum circuit is the key idea behind the probabilistic error cancellation, in a way similar to zero noise extrapolation. And here you see a way to write, in terms of different gates, the unitary relevant to the ideal quantum circuit. And we can exemplify the idea of estimating a result, the ideal result, based on taking the measurements of the trace of the observable of interest times the initial state of the system to which a unitary of a quantum circuit has been applied. So, as mentioned earlier, what we're applying actually, even if that's what we see in the quantum circuit scheme, is not what happens on the real device. So what can be done with probabilistic error cancellation is that we can say, okay, we're never going to apply this ideal unitary, but instead we can, and the same is done for the single gates. But what you can think is that actually what we're applying are noisy gates, and it's a set of noisy gates that we can explore by changing some parameters of a quantum circuit using different, well, this is called the negativity of a quantum gate, but basically by expanding the ideal quantum gate onto a basis that is a linear combination of noisy quantum gates. And then we sample the noisy quantum gates, and based on a noise model, we're able to retrieve or estimate the ideal quantum gate. So you see that probabilistic error cancellation is a quantum error mitigation techniques that is happening with the estimation of an implementable better quantum gate at the quantum gate level in quantum circuits. And once again, taking again the workflow that I've shown before that applies to all these techniques, the idea is that you have a probabilistically sampled circuit, many of them that are executed on the back end, and then based on these many measurements, we perform this linear combination estimate, and we mitigate the expectation value. It's always these two passes. And this is what probabilistic error cancellation looks like in Mitiq. So you see that the quantum gate in the top is represented, in this case, for example, assuming a noise model, as I mentioned, locally polarized noise, in terms of a combination of different gates here with prefactors that are basically these eta, I, alpha. So this is just one part. I don't show the full application of probabilistic error cancellation, but this can also be executed with a single line, which you see here, execute with probabilistic error cancellation imported from Mitiq. And actually what we see here, it's results from a simulator of different, of like 0 is the PC value, and it's also the real value that we wanted to estimate in this test. And in this case is what we would have obtained with an unmitigated value. And this is like a statistics of the samples. So as you can see here, there is an overhead on the number of quantum circuits that you need to launch on a quantum device to be able to apply probabilistic error cancellation, which is one of the downsides of this technique. So I'm really over time. I cannot get into the details of this other technique, which is called Clifford data regression, but I can briefly sketch what it is about. So the main idea is that the quantum circuit of interest is generally interesting because it has some non-Clifford gates. Like I remind that Clifford-based quantum circuits are efficiently simulable on classical devices. So if everything is Clifford, it's not interesting from a quantum perspective. So let's assume that we can replace, without modifying too much, the non-Clifford gates with Clifford gates. Of course, we're going to modify the quantum circuit, but we obtain a different training set of circuits, of quantum circuits, that then we can use to learn how to correct to the exact value based on a noise model that we have. So this is the main idea behind Clifford data regression, is a learning-based technique in which we train our error mitigation technique on a subset of model that is actually not the original data set of the quantum circuit with the non-Clifford techniques. But once we have created the fitting model, then we use it to mitigate errors on the original quantum circuit. I know it's a wavy, but there is no too much time to get into details. And again, I just want to show from this workflow that the workflow, it's similar in all cases, like generate a bunch of circuits, execute them on the back end, and then provide some inference. In this case, we have an initial step of training the quantum model, training the inference model, executing first on an efficient classical simulator, a modified set of quantum circuits that are efficiently simulable. And in this case, it's a variable noise Clifford data regression technique. So it has also some subtleties that you can read in the documentation. So finally, I can speak about digital dynamical decoupling. Some of you that know about control theory, quantum control theory, and pulse level control may have heard about dynamical decoupling. So dynamical decoupling stems from the idea that you can apply pulses at the pulse level to your qubit. It actually originates from an NMR technique, and it was originally not even called dynamical decoupling. So you apply pulses to your qubit in order to decouple it from the environment, so that on a time span that is actually on a time scale generally shorter than the time during which errors kick in due to the environment, you're able to operate on your qubit and you dynamically decouple it from interaction degrees of freedom of environment. So again, here the challenge with Mitig was, can we apply this pulse level technique in which you apply, for example, single qubit pulses to decouple them from each other and from the environment sorry, not from each other, just from the environment to into Mitig at the digital level. And this is a sketch of the workflow, as always. So we actually compile different digital dynamical decoupling sequences, exploiting idle windows in which nothing happens on a given qubit. We execute on the backend, and basically we already have the result, because the inference is trivial on dynamical decoupling. It's already the result that we get from the execution. And so here I just want to show another snapshot from the documentation of Mitig, actually, of this is the original circuit. It's just shown for instructive purposes, with a series of X gates and then swap gates and CNOTs applied to the circuit. Here, 7 qubits. And here you see that after inserting the digital dynamical decoupling sequences, we are inserting sequences where we have space, using actually a rule that in this case, it's an alternating sequence of gate X, Y, X, Y, because actually we don't want the state of a qubit to be changed by the application of a dynamical decoupling sequence, but only to be decoupled from noise. Next, I want to point out that the effort to port the digital dynamical decoupling technique into Mitig was led by Aaron Robertson, who's a quantum enthusiast and is a member of our extended community, and that in 2021 became a Unitary Fund ambassador due to the involvement and enthusiasm and valuable input that he provided to the project and to the community. And yeah, I'm really excited by the fact that digital dynamical decoupling has just been ported to Mitig, thanks to this contribution from the community. So, Abu, I think I just have 6 minutes for questions.
You have 0 minutes, but we can take a few
okay,
questions.
0 minutes. So
one
I will
minute.
just, yeah, I will. I think I will just skip. Yeah, we can skip this. This slide.
We can get the questions. Yes.
Yeah, let's get the questions. Let me just. I'm sorry, I have to go through all these slides, but I want to.
No, it's very inspiring.
I just want to mention this. Yeah, I just want to mention this.
Okay.
So I didn't have the time to go through the research results, but you can look at them on the Unitary Fund webpage, unitary.fund/research. I want to mention there is a summer school in Florence that has an hybrid approach and can be in person or online, and applications are open. This is part of the SQMS framework coordinated at Fermilab, in whose ecosystem Unitary Fund is based. So there will be an error mitigation lecture and lab in one of the last days by Andrea, Mari, and me. So please apply, because there is also support for some students, I guess only from the US support, but the online conference should be, the online summer school should be free for everyone to attend. So yes, finally, let's again reminding you to join the Unitary Fund community for the Mitig community calls and other group calls. This is a snapshot from the recent Unitary Hack maintainers meeting. on Friday at 6 p.m. this week, we will have the Unitary hack kickoff day. And yes, with this, I end my talk, and thank you for your attention.
Yeah, thank you for this very inspiring talk. I think this Mitig is also a great idea. It brings science, technology, software, community all together. I guess it's also mature enough. Maybe we can put the education in the picture, somewhat maybe education for it, or just some projects, etc., some pedagogical. Okay, there are one technical questions. They want to, some of them want to see or access this presentation. If you share with us, we can post on the Discord. Nathan, it's up to you.
Sure. Yeah.
Okay, if you send me by email or other organizers, we can put it. During talks, Syed asked a question about error mitigation, kind of filter out the noise from the final output. So this, yes, do you agree? It's kind of post-processing. Error mitigation means once you get the results, then you are doing kind of post-processing, or it is more than this.
Sorry, could you repeat the question, because I was trying to read it, but I could not find it.
It's little up. Filter out the noise from the final output. Filter out the noise from the final output.
Yeah, I would say that we could think of trying to filter out the noise, but more than filtering out the noise, which is something that it's done, let's say, with dynamical decoupling. These techniques learn more about the noise and the result that occurs when increasing levels of noise are involved, and then tries to adjust for it, as you said, with the post-processing technique. And also to answer to Zoltan question, we have a very basic readout error mitigation module in Mitiq, which is based on post-selection. So basically, if you know that your bit string should have a given attainable result based on the symmetry of the problem that then translates to the quantum circuit, you can already discard some of the results, and this way build another statistics. But it's there's also like more elaborate techniques, also based on symmetry-based copies for readout error mitigation. So that's actually a focus of development for this year. So I don't know if Zoltan is interested, or anyone who's interested, please join my Mitiq calls or on GitHub, because that is something that we wish to implement in Mitiq in 2022.
Okay, thanks, I will.
Okay, there are a few more questions, Nathan, so it was really interesting. Marco asked one question.
Yeah, maybe I can directly
ask directly.
So thank you for the presentation. So my question is about generally NISQ. So the way I understand near-term algorithm is that we have noise, it's a problem, and so we can do technique to increase the depth a little bit of the circuit, but at some point it breaks down. We cannot scale up. So are you aware of some technique in which, for instance, you have algorithms that are scalable without error correction, in the sense that by smart design of the circuits, you have more noise, but the noise propagates in such a manner that you can keep an exponential advantage while having the noise. Does that exist, or it's always, it's never asymptotic behavior, just in practice? You see what I mean?
So this is a part of the study in error mitigation. So about the asymptotically exponential advantage, it depends, because especially for NISQ algorithms, I am not aware of asymptotic advantage. But I mean, there are some results, and this idea of shielding from the noise, in some cases, also based on, for example, embedding early on into an Hamiltonian that is resilient to specific types of noise once, for example, upon totalization into quantum circuit of a quantum gates. So playing with symmetries, it's also something that is done and has been proved also on hardware.
Okay.
When you talk about the exponential advantage, the catch here is always that there's always generally an overhead. And this overhead is in the fact that you have to sample much more.
Yeah.
And so then you have to take into consideration the sampling time, and so the shots that you need to launch on the machine.
Okay, yeah, I had in time, like you need more shots, but for instance, only a polynomial extra number of shots while you have exponential advantage, and then you keep having it. That's the thing I was thinking of, and I wondered if it exists, but
so there are some research papers, for example, from Kai in Oxford, and yeah, there are some proposals. For what I've seen, it's mainly proposals, theory proposals, and not yet experiments, or in some cases like experiments, but of limited scope in general.
Okay. Thank you.
You're welcome.
Okay, Karam has a questions. Maybe you can answer shortly. Can neural networks be applied to enhance the Mitig module?
Yeah, that's a great idea. And we actually started very simply. So we see different ways in which neural networks could be, I don't know if it's quantum neural network or neural network in general, but let's say neural network in general, a way to learn a better inference model could be through neural networks. And so the learning-based approach that we mentioned in Clifford data regression is, for example, the first case in which one can envision applying a neural network approach to do this training and learning. But in most cases, we try to do things as simple as possible, because sometimes neural networks involve like another black box, and we want to limit the amount of black boxes in the problem. But yeah, it's definitely doable.
Okay, Victor Torres has a question. Is there a method for error mitigation using cross operators instead of master equation?
Yes, definitely. So yeah, let me also point out that the master equation that I've shown actually was a theory framework to provide insight into the time evolution of a system. But most of these methods do not require a master equation level formalism of to study the evolution of the system. So this was like what I thought was like the simplest way to illustrate the action of noise at the superoperator level. But for example, you can show noise at the quantum trajectory level on single states. And so density matrix formalism is not required. With respect to cross operators, I imagine that the question hints at different, like the composition of the quantum circuits or quantum channels that can be used to picture the evolution of a quantum system. Yeah, and that's also something doable. Actually, it's done in most cases. Like the quantum noise model can also be exemplified at the cross operator level.
Okay, we already exceed 10 minutes. Nathan, I know that you will not be available after today, but will you able to join Discord? Maybe we can copy paste these questions and you can answer there.
Yeah,
if not,
sure.
I can ask by emails and then copy paste your answers. Which one work better?
Yeah, let's do also Discord. That would be great.
Okay, then the next questions we will copy paste to Discord, and Nathan will try to answer them today. Okay, thank you very much, Nathan.
Thank you. Thank you, everyone.